kind of multiplier, current multiplier. There are two cells that we talked about, and one such cell is an important cell, and that is depicted here. You can see how this forms the translinear loop. T3, T4, T1, T2 form the translinear loop. Type A and type B cell we had drawn last time. This is the type B cell, where now we are trying to input signals and see what happens to this cell in terms of the signals that are inputted. The common base point is connected to a base potential, arbitrary base potential. Okay. This VB is an arbitrary base potential with respect to ground. Now, let us see how this circuit behaves. This is called Gilbert's gain cell, and this concept is very important in VLSI design, analog VLSI design particularly. The cell should be always something that can be used to build a superstructure. It should be such that it should be identical in its nature when we build a superstructure with this kind of cell. Let us see whether that characteristic is present in this particular cell. Let us now see the relationship. Let us see how the current relationship is there. IA1 is the current flowing in this into, let us call the current flowing in this as I1, the current flowing this through this as I2. So, IA1 into IA1 into what? I1, right, is equal to, again IA2 is flowing through this into I2. Is this understood? Based on translinear principle, current flowing through the counterclockwise diodes will be, product of those will be equal to the current flowing through the diodes which are clockwise. So, IA1 into I1, okay, is equal to IA2 into I2. This is the basic current multiplication relationship. In this context, let us see how this can be used for current amplifier. So, IA1 divided by IA2 therefore is equal to I2 by I1. The ratio relationship is clear from this. IA1, look at it, divided by IA2, we will call these as input currents. The ratio of the input currents IA1 by IA2 will be equal to I2 by I1, I2 by I1. I2 and I1 will form the part of output currents. Okay. So, the ratio of input current is exactly equal to ratio of the output current, and this relationship is valid, as I told you, over a large magnitude of variation of current. It is not a small signal relationship. So, from maybe microamperes to hundreds of milliamperes, this relationship is valid. So, now suppose we write it as IA1 minus IA2 divided by IA1 plus IA2. What is it going to be equal to? I2 minus I1 divided by I2 plus I1, the ratio relationship. And we have I2 plus I1 always equal to a constant current, DC current, which is I naught dash. So, if we say that IA1 minus IA2 is the differential input current, IA1 and IA2 are two input currents. Okay. Whenever we have two input currents, like in the case of two input voltages, we can have a differential input voltage. When we have two input currents, we can talk of a differential input current and a common mode input current. Any current, therefore, IA1 can be split up as a current common to both. What is it? IA1 plus IA2 by 2 plus IA1 minus IA2 by 2. This is the differential part. So, any current IA1 can be split up as a common current common to both, plus half of differential part. Similarly, IA2 can be written as same common current IA1 plus IA2 by 2 minus IA1 minus IA2 by 2. This aspect of common mode and differential mode current, or common mode and differential mode voltage, has already been exposed to as far as you are concerned in differential amplifier. Same thing can be thought of in terms of currents. So, what does it mean? I have a common current here which can be made a DC, and the differential current can only be kept as signal current. So, suppose this common current IA1 plus IA2 by 2 is a DC. Let us call that as, let us say, I0 dash, I0, let us say I0, because I0 dash we have called this current. So, we will call this as I0, the common current. The common current I1 plus I2 by 2, I1 plus I2, we are calling it as I0 dash. So, if I say IA1 plus IA2, okay, is equal to, let us call it as I0, a common current, then we will, in order to keep it in line with this, I1 plus I2 is equal to I0 dash. Similarly, IA1 plus IA2 we will call it as I0, thereby this is I0 by 2 we will call it. That is, but common current is a single value, whether you call it I0 or I0 by 2, it does not really matter, it is a single current. So, I0 by 2 plus the differential current, I0 by 2 minus the differential current. So, what happens to this relationship now? IA1 minus IA2, that is the differential current divided by IA1 plus IA2, which is nothing but I0. This is equal to I2 minus I1 by I0 prime. This is an important relationship. If you notice this relationship, we will see something very nice emerging out of it. I2 minus I1 by I0 prime, therefore, I2 minus I1 equals, what is it? I0 prime by I0, which is nothing but ratio of two currents, ratio of two DC currents. So, what happens? It is a constant, it can be controlled by us. Let us come back to that later. Ratio of two currents into IA1 minus IA2, the differential input current. So, this is an important relationship in what is called as current mode amplifier. So far you have been exposed to voltage mode amplifiers. Why can't we think amplifiers as current mode amplifiers? And that seems to be more basic, and that kind of amplification can be done easily compared to voltage mode amplification. Look at the way you have obtained it. Differential input current times a gain factor is equal to output current. Now, this gain factor is not something very simple. In fact, this gain factor is absolutely constant, because we have already known that we can obtain a current ratio by what? How do I obtain a current ratio? I can obtain a current mirror, I can generate a current reference, okay, and I can obtain any current ratio by area ratio. So, I can see to it that this ratio of current is going to be same as ratio of areas, which means it is just geometry dependent. That means absolutely constant, independent of temperature, supply voltage, everything. This is what you have been trying best to achieve in the case of voltage amplifiers, which you have failed to achieve in a simple manner, which you could achieve only by using feedback, etc. Here there is no feedback at all adopted. Without using negative feedback, I have been able to demonstrate to you that we can get a amplifier, current amplifier, whose amplification factor is absolutely constant. Is this that's why this Gilbert gain cell, even though it was proposed way back in 1970s, its prominence was never understood at that time. But in a VLSI context, analog VLSI context, you see that this gain cell is the most important concept ever to be given to analog circuitry. Why? First of all, its dynamic range is fantastic. There is no other amplifier whose dynamic range can be as high as this. Okay? Then it is independent of device property like beta, etc., device parameters, and that you are achieving without negative feedback. If you don't do it without without negative feedback, right, what will happen? If you don't adopt negative feedback, then all the problems associated with negative feedback, like need for frequency compensation, all these things are not existing, and therefore this concept can be adopted for designing what are called as wideband amplifiers or video amplifiers. This basic concept is the concept that can be straight away adopted for video amplifiers or wideband amplifiers, okay, because there is no need for negative feedback, and if there is no need for negative feedback, there is no need for negative feedback because of the fact that amplifier gain is independent of device parameters. And if you do not have negative feedback, then the consequent problem of frequency compensation being needed and oscillation to be prevented, all these things are avoided. Now, apart from that, look at the structure. This is the input current. What will be the output current? Differential output current? IB1 minus IB2 is the differential output current. IB1 is equal to IA1 plus I2. IB1, IB2 is equal to IA2 plus I1. What does it mean? This is equal to IA1 minus IA2 into 1 plus what? I0 prime by I0. This is like your non-inverting amplifier. So, differential output current is equal to 1 plus I0 prime by I0 into IA1 minus IA2, and this can now become what? Please complete this. This can now become, okay, IA1 and IA2 for the next stage, which is exactly identical to this, only that it should be operating at I0 double prime, which is higher than I0 prime, in order to get a gain factor. So, this can become now the input current to another identical stage, which will come here, the input current, and the output of that will be what? Again this as the input current into 1 plus, let us say I0 double prime by I0 prime. So, now you can put this cell over another cell and keep on building your structure of current amplifier until you reach the power level of current that you desire. You can go on doing it. So, this is truly a cell structure needed for VLSI design, right? Because the structure looks exactly identical, and it can be put one over the other and you can build a superstructure. Is this clear? So, you go on doing this and then where do you stop? Suppose you reach the current level that you desire, then you can now convert this into a voltage simply by putting resistors, two resistors to the final supply voltage and take the differential output. So, converting a differential output current into voltage is simply by putting resistors. So, that is not a problem at all. So, this is what is done here, and it is truly wideband primarily because you are at all times dealing with only currents, and the voltages involved are only diode voltages, and therefore, the capacitors to be charged will be those capacitors across the diodes, and therefore, they are to be charged by a very small magnitude of voltage, and therefore, it is going to be very fast. Okay. So, that means current mode of operation is always fast, because in the case of voltage mode of operation the capacitor have to be charged up to a certain value of voltage. In this case, since you are operating in current mode and the voltage is always equal to the diode voltage, you do not have to spend time in charging the capacitor. So, that is why please remember the current integrated circuit design deals primarily with current mode operation. So, that is quite suitable for all design of circuits of analog VLSI systems. Now, this aspect of Gilbert's gain cell, that is why we are calling it Gilbert gain cell. We will later see how it can be used as a multiplier, precision multiplier, when we start discussing about multiplier. Is there any doubts so far? Things are clear. Okay. Like we do namaskaram to Vinayaka before proceeding with any work. When I started discussing about amplifier, I had to bring about this important concept of current amplifier by Gilbert. That is, Gilbert cell has that pride of place. We have to preserve that pride of place for the Gilbert cell as a current amplifier. Even though this has not yet become popular in design of ICs, it is going to become popular in a very short time. Now, we will go back to the conventional amplifier, which is always treated as a voltage amplifier. This we had discussed earlier as an inverter. In our digital circuit, we said the bipolar inverter or MOS inverter is the basic stage, which can also be used as an amplifier. Let us see how this inverter is suitable as an amplifier. This is a basic transistor amplifier, which is called common emitter amplifier. All of us know about it. Vi is the input signal, and V naught is equal to VCC minus IC times RC, and that is equal to VCC minus alpha times IE, and IE is in turn equal to IE naught exponent Vi by Vt, and therefore, that into RC. So, VCC minus alpha IE naught RC into exponent Vi by Vt. So, this we already know. This is an exponential, therefore, relationship between output and input of a transistor stage, basic transistor stage. If we plot this, how will we see this? This we had already seen in our discussion about digital inverter. Now, let us see how it looks like when we discuss its characteristic in the case of amplifier. When IC is when Vi is very small, this is equal to VCC itself, and therefore, it will start with VCC. Then as Vi keeps on increasing, current will keep on increasing, and therefore, this is the kind of character, this is the exponential characteristic, as current keeps on increasing, the output voltage here keeps on decreasing. Finally, the transistor will enter the saturation region where it is absolutely useless. That is, the moment this voltage reaches about this Vi plus V gamma, or Vi let us say Vi plus 0, that is VCB equal to 0 is the point where it is entering the saturation region. So, this collector base potential should be reaching 0, or VCE should be reaching V gamma. Okay. So, that is when it is entering the saturation region. When it is getting forward biased, both the junctions will be getting forward biased. So, the voltage will be of the order of 0.1 to 0.2 volts. So, this is the state of affairs as far as this amplifier is concerned. Now, we are interested in operating this in this region. So far in the digital circuitry, we were interested in operating it either here or here in the steady state. It was only transiting from here to here when it was going from high to low or low to high. Whereas, in the case of amplifier design, we are going to operate it in this region. So, somewhere here, let us say where the gain is going to be pretty high. Gain is nothing but the slope delta V naught by delta Vi. So, gain is nothing but the slope, that is nothing but delta V naught by delta Vi. So, let us see this. As far as this is concerned, we have this as VCC minus alpha times IE naught. Now, RC exponent Vi by Vt. In order to make this get located somewhere here, so that it can act as a good amplifier, I have to apply what is called a bias voltage. So, that if I do in terms of voltage, let us say it will be VIQ, some quiescent voltage, plus the signal voltage which is delta V divided by Vt. So, what happens here? This is VCC minus alpha IE naught, then exponent VIQ by Vt into RC exponent delta Vi by Vt. So, what is alpha IE naught exponent VIQ by Vt? What is this value? IE naught exponent VIQ by Vt is IEQ. IE naught exponent VIQ by Vt is nothing but IEQ, quiescent operating current, and alpha times IEQ is nothing but ICQ. So, this entire thing is nothing but ICQ. This is therefore VCC minus ICQ into exponent delta Vi by Vt into RC. So, we see here that this is VCC minus ICQ RC. Okay. What is exponent delta Vi by Vt? 1 plus delta Vi by Vt, 1 plus x plus what? X square by 2 factorial, so on. So, in an amplifier which is supposed to be linear, delta Vi when it varies, okay, output should vary according to delta Vi. So, that means all the other terms should become very small. These are the non-linear terms. So, what is the condition for this to be a linear amplifier? We can see that delta Vi by Vt has to be much less than 1. So, this is an important relationship in the case of a bipolar transistor, that delta Vi by Vt should be much less than 1, okay, irrespective of the operating point. Okay. So, that means if delta Vi by Vt is very small, then the nonlinearity resulting in the exponent is going to be minimal. It does not mean that saturation as well as cutoff nonlinearity will not come into picture. Those things are to be separately taken into account. If saturation and cutoff nonlinearities do not come into picture, then the nonlinearity resulting due to the exponential relationship is going to depend upon only delta Vi by Vt magnitude. Delta Vi by Vt should be made very small compared to 1. That was the assumption, that if delta Vi is a sine wave, then immediately we know that there is predominant second harmonic distortion in this because of the square term. This also is to be noted clearly. The predominant second harmonic distortion is responsible for the first instance to cause final distortion. What is this therefore equal to now? VCC minus ICQRC is nothing but VCQ. VCC minus ICQRC is nothing but VCQ minus ICQ RC into delta Vi by Vt, that is the wanted term. That into 1 plus rest of the term is the nonlinear term, which has to be made very, very small, which is nothing but delta Vi by Vt to Vt. So, we want this factor to be very, very small compared to 1. Strictly speaking, is delta Vi by 2 Vt, which should be made very small compared to 1. So, what is this? ICQ RC divided by Vt, nothing but the gain, which we have been calling as VCQ minus Gm, the transconductance of the transistor, into RC into delta Vi. So, you can see that phase shift coming about, that when Vi increases, the collector voltage is decreasing. So, you see the phase shift of 180 degree and also the gain of Gm into RC coming into picture. Okay? This is clear. Now, this amplifier is not good enough for us. Look at the problems associated with this amplifier. First of all, I have to bias it at a voltage which is VIQ, then superimpose over that the required signal set of FR. That VIQ should be of the order of 0.5 to 0.6, and that itself should not change. Suppose I am able to get a voltage source of that type, I can bias it. But even if I bias it, we know that this voltage itself is going to keep changing with respect to temperature. What is the coefficient of this voltage delta, that VBE? VBE changes with respect to temperature in a manner which is minus 2 millivolts per degree centigrade rise in temperature. You know all this, right? A diode which is forward biased has a temperature coefficient of minus 2 millivolts per degree centigrade rise in temperature. That is delta VBE by delta T, that is the temperature coefficient of a diode, which is going to result in, even if the signal is not varying, if the temperature is varying, what will happen? This collector voltage is going to drift. That is the problem of drift. So, because VB is changing with respect to temperature, the output voltage is changing even though input has remained constant. Input has not changed. So, output changes with respect to temperature and consequently with respect to time. So, it keeps drifting with respect to time because of its dependence on temperature. This is the major disadvantage of this amplifier, particularly for low frequency signals. This is going to be a nuisance. For high frequency signals, at least I can decouple this, okay, and only extract the high frequency part and couple it on to another stage. So, it is not going to be a problem, but for low frequency signal this is going to be a problem. So, that is the reason this stage is not preferred in integrated circuits. In integrated circuits, we would like to exploit the property of the device to compensate for this. Straight away, I would say that one technique is to see to it that this is modified somehow. And in an amplifier, when I give an input signal, I would like to give it straight to the input of the input terminal of the amplifier. I do not want to couple it again through capacitor, etc. So, that means preferably I would like the amplifier input voltage to be 0 when the output voltage is also 0. Okay. If the input voltage, when it is non-zero, output voltage is also finite, okay, for some reason because of operation, etc., then there is what is called as what? Offset. The only way I can make the input when it is 0, output to be 0, to become the operating point is to see that the device works both with plus as well as minus supply. Otherwise, I cannot say with the single supply, you can see that output has to be always somewhere in between, which means it has to have an offset necessarily. That means when the input is 0, output is not going to be 0. So, in a true amplifier, I would like the output to be 0 when the input is 0, or I should be capable of connecting the input directly to the ground when there is no input. So, what do? I use another supply. So, the dual supply concept comes, okay, if you want to get rid of coupling the whole circuit by means of a capacitor, and capacitors are things which have to be avoided in integrated circuit. They are not available, okay. Even though they are available, they are available with very small values. They have to be cautiously used. They take up lot of area, and therefore, this concept of biasing it by means of another supply, how do I bias it? Now, I can put a negative supply, but I just told you that it is easier to supply a current into it and force the voltage. So, I would rather apply here a current. So, using a current source. Now, what happens? Automatically, I can make sure that this can be grounded now. When the signal is there, not there, this can be grounded simply, and automatically it gets biased by the required voltage in order to carry this current I e. In order, this is the emitter current. In order to sort of say that this current is something that we are obtaining from another current source, we will call this as I naught. Now, I have biased it by means of a current, whereas biasing it by means of a voltage is a very troublesome affair. First of all, I have to get the exact voltage, which is very difficult, and even if I get the voltage, it is going to drift because of temperature variation. Whereas here, the current emitter current is fixed, and even if the transistor base to emitter voltage drift, nothing happens as far as output current is concerned, quiescent current is concerned. So, biasing by a transistor by means of a current is preferred to biasing the transistor by means of a voltage. So, I would rather bias it by means of a current in this following manner. Next, you will see that obviously the emitter has to be grounded, otherwise it cannot be common emitter amplifier. So, how do I ground this? For AC it should be a ground, or for signal it should be a ground. So, normally in a discrete circuit I would have put a capacitor, which is called a bypass capacitor, but this capacitor for low frequency operation has to be very high in order to act as a short circuit at that frequency. But in an integrated circuit, what should I do? So, in an integrated circuit, I should not use a capacitor, but I should use a dynamic impedance which will act as a short circuit for signal, but it will not disturb my biasing current, okay, so that I still know what the biasing current is. As long as I know what the biasing current is, that is called stable biasing. If I am not able to tell you what the biasing current is, that is called unstable biasing. Suppose I ask you, please tell me the beta of the transistor, only then I will come up with the biasing current, then it is unstable biasing. If I say, look, I know what the biasing current is going to be irrespective of the transistor parameter, then it is called stable biasing. In this case, therefore, I have to put a device here. What will be the device that I will put? Automatically I will put a forward biased diode here. Please understand this, because a forward biased diode is a short circuit for signal. But what will it do to this current? Because of the IC property, the I naught is going to be split equally, because bases are connected, emitters are connected. So, these are identical transistors, and therefore, the currents have to be equal. So, that principle that we depend upon so much in integrated circuit, that when the transistors are equal, okay, and if the base emitters are at the same potential, then the current should be equal, is what is used for biasing it in a stable fashion. That means the biasing is not going to be disturbed, it is going to be I naught by 2. I am able to tell without any hesitation. That means it is a stable biasing. And apart from that, what have I achieved? As far as the signal is concerned, it is going to act as a near short, not exactly a short. What is the impedance from that emitter to ground? Incremental diode impedance, which is small re itself, and therefore, this is going to still act as an amplifier, okay, which is very similar to common emitter amplifier, with the gain now being reduced to half, because it instead of being a short circuit, it is also Re. So, this Re of my common emitter amplifier and Re of this diode will share the input voltage. Okay. So, earlier input voltage was totally coming across base to emitter junction of the amplifier. Now, base to emitter junction of the amplifier gets only half the input voltage, because Re of this amplifier as well as the diode will be sharing the input voltage. When the input voltage is fed here, Vi by 2, Vi by 2. So, you can see here that the operating current is going to be I naught by 2, I naught by 2. Then I say, in order to have the early effect also the same, if the early effect, what is the early effect? Collector base voltage is going to still determine the collector current. So, if collector base voltage also happens to be the same, then I make sure that the current division is equal, and therefore, what do? I also connect this so that it also has the same collector base, because otherwise I will have to leave the collector hanging. Instead, I will as well connect the collector resistance through the same valued resistance Rc to the supply. Now, what is this? This is nothing but the difference. I mean, this is one way of presenting differential amplifier. It is not how this has developed. Is this clear? This is one way of presenting the differential amplifier as something that has originated out of necessity of getting rid of the disadvantages of discrete common emitter amplifier when it is being adopted for IC version. So, when you are adopting a common emitter amplifier for IC version, we can say that we want to get rid of the bypass capacitor, we do not want coupling capacitor, and this is one way you can get rid of coupling capacitor as well as bypass capacitor in any discrete circuit, and this is one important powerful technique of converting every discrete circuit into integrated version. Is that understood? Any discrete version of a circuit that you have can be easily converted, getting rid of all the bypass capacitors simply by making it differential. Okay. This is a powerful technique. So, you have to understand this technique, and therefore, I brought it out. Now, once you say that this is going to be differential, what happens here? This current is going to remain constant I naught. If signal voltage gets dropped here as V I by 2, and this will be minus V I by 2 superimposed over V I Q. Okay. This will be plus minus, okay, minus V I by 2, and therefore, it will develop a voltage which will be in phase opposition to this, but of the same magnitude, and therefore, if this is minus GM RC, okay, this will be plus GM RC here. Okay. And the GM in this case is how much? 1 over 2 RE, not 1 over RE, because the voltage, input voltage, is divided between two diodes. So, Vi by 2 Re into Rc is the single stage gain with a minus for the first stage, and for the other stage it is plus Rc divided by 2 Re. Is that clear? So, if you take therefore the differential output here as the output, what will you get? One is going to be minus Rc by 2 Re, another is plus Rc by 2 Re. If you take the differential output, it is Rc by Re or Gm into Rc. That means you are getting back the common emitter gain which you had thought you have lost it because of converting this stage into a differential stage. So, you have not lost anything at all by converting this single stage into a differential stage. It retains all the small signal properties associated with the common emitter amplifier. The gain remains the same, but it has advantages now. Output voltage can be made equal to 0 when the input voltage is 0. Okay. That is because of the fact that we are using the dual supply. That is what brings in dual supply in all analog circuits. Okay. And then we have got rid of the bypass capacitor and the coupling capacitor. So, we will discuss further about this important building block. This is the most important building block again in analog integrated circuits, next to current mirrors, next to translinear principle. It is part of the translinear principle. Okay. So, tomorrow's class we will discuss more about this. Already you know something about this, but we have to spare our complete efforts in sort of understanding it fully, so that we know about this basic building block.